Right, recording is rolling. It is Tuesday, April 30th. We're going to continue this quantum mechanics journal. So yesterday where we left off, we're looking at these four fundamental forces, which is kind of a setup for next one we're going into, which is going to be the standard model. All right, so you guys then remind you guys where we left off. Right, there are these considered to be these four fundamental forces. Now, if you remember back to general relativity, you can actually make a case that gravitation is not actually a force, it's just an artifact of warping of space-time, right? Which actually kind of lines up better with the standard model, because the standard model actually predicts these other three uh, fundamental forces. Right? So, but anyway, if you Google four fundamental forces, then probably get something like that there. Right. Right. So next one we're doing is standard model. I'll play you guys a video for this too, but let's take a look at this. Right. So if you ask a chemist what makes up everything in this room, they'll point at the periodic table. Right. And the periodic table is organized a certain way and based on valence electrons and chemical properties. Right. But then you say, well, hold on, aren't all those elements just made out of protons, neutrons, electrons, right? So maybe isn't it like three things, right? Go talk to a particle physicist. They'll say, yeah, okay, you're a little bit closer, right? So electron actually is an elementary particle, right? So that's here, right? But protons and neutrons actually you can break down even more, right? So it's a combination of up and down quarks. I'll put that in the notes too, right? Actually, there are these other particles too. Right? You guys call it a photon. Hey, photons on here too, right? So this was a model that was worked out mathematically by theoretical physicists go back to the 1960s. And ever since then, experimental physicists have been working at particle colliders to uncover these particles experimentally one by one. All right, so with that intro, I flip over here and find the video for. There you go. Ooh, all right. So let's go back over here. So here's what we got for the organization of this model, right? So you ask a particle physicist what's the fundamental particles, and they'll point to the standard model, right? Which again worked out by theoretical physicists back decades ago. Right? We got 6 quarks and 6 leptons. These are considered to be fermions. We'll see that term show up later. Okay. And then we got these in pink over here, put these 5 force carriers called bosons, right? Which actually align with these fundamental forces over here, except of course for gravity, which is not part of the standard model. Right? So what's the connection there? Okay. And how are these organized? Right, so they're organized by mass, charge, and spin. Mass, charge, and spin. Right. Right. A couple other details put on here is what makes up protons and neutrons. Right. So a proton is actually a combination of 2 up quarks and a down quark. Right. A neutron, right, which is got 1 up and 2 down quarks. Okay. Electron is elementary. Okay. So that actually is truly a fundamental particle, elementary particle in electrons. And so yeah. Right. Now that video I just played you guys is a bit outdated because he mentioned in there that, we haven't actually like experimentally verified this Higgs boson. I think he said we hadn't actually discovered it yet, right? Again, for decades, mathematically it should be there. We actually have, right? So back in 2012 was the year, back in July 2012, it was finally experimentally verified that Higgs boson exists, right? But what's like, first of all, what is this, right? What does it have to do with this Higgs field, right? It has something to do with giving particles mass. I've got a video queued up for guys, right? And what does it mean to discover a particle at all, right? Maybe Higgs boson was the last one to complete the standard model, right? But what about like any of these fundamental particles? What does it mean when particle physicists are discovering these, right? So with that, all right, got a few queued up for you guys. Ooh, all right. So all those diagrams that were just flashed on the screen and it just paused random. So those are called Feynman diagrams, and they're showing particle interactions, which is also one of the quadrants we're going to do. So, all right, no, that was a bunch right there, bunch of info. So, go over this with you guys. All right. So, what is this Higgs boson? Well, it's actually an excitation in this everywhere permeating Higgs field, right? And that's what quantum physicists, particle physicists use to explain why anything has mass, right? So anything that does not have mass, like photons don't have mass, always travel at the speed of light. Hey, right, because light's made of photons, right? And then if you remember back to relativity days, that might have some interesting consequences too, right? So if you're traveling at the speed of light and run Einstein's relativity equations, you can make the case that space and time really don't even exist from your point of view. So what does the world look like? What does the universe look like from the point of view of photon? Interesting question, right? But we don't have to worry about that ourselves because we have mass and we get to experience space and time and not moving at the speed of light. All right. All right. So particles that interact with this everywhere permeating Higgs field are given mass, right? And then there's electron fields, in this case Higgs field. Right. So this Higgs boson is an excitation in the Higgs field. Right. This was experimentally verified in 2012. Right? And when particle physicists say they've experimentally verified something, that means there's well, I'll say less than 1 in a million chance of being random information. Right? Like a lot of science realize I'm reaching conclusions that are statistical in nature. Right? You might have some psychology hypothesis or maybe some economics idea, right? Where maybe the nature of your research is, well, I have to gather lots of data and crunch the numbers and do some probability analysis on it, right? So yeah, if you're going to be a hardcore scientist, then yeah, statistics is going to be one of the most important classes that you take, maybe for that reason. Right? So what's the standard? What's like the scientific standard for publishing? Right? You guys got all that? Because this is going to bring us back to this normal distribution curve that, hey, I showed you guys a few weeks back. Right? You guys remember this normal distribution curve? Okay. So for you guys, the context, one thing I had you guys do was say, like, measure your height and your friends' heights and say, like, where do you say, like, stand in the big scheme of things, so like in the population, right? Suppose you were 1 standard deviation above the mean. Okay, that means you're maybe taller than most people, but shorter than a good number of people too, maybe something like that, right? Right. Now, say like a scientific discovery, suppose you run some scientific experiment in some field, okay, and you have a null hypothesis that, okay, I think this is maybe like if I were incorrect in my hypothesis, then this is how the world should work. But if I'm correct, I think things work differently than that. Then I would like to disprove the null hypothesis. Okay? So what's a conventional scientific standard? Usually beyond 2 sigma, 2 standard deviations beyond the mean, right? If you're consistently getting data that, if it were random, it would be beyond 2 standard deviations, then that's usually strong enough to publish and say, hey, I think I really discovered something here. Right? But 2 standard deviations, if you guys remember from your Z table. Well, let's look at the Z table. What is 2 standard deviations? That's like 97.7% going on right here, right? So it's about maybe about 2.5% chance of it being random, right? There's a good case to be made. This is actually like an issue out in the scientific world that a lot of published science might possibly just be this just randomness, right? Like, if there's a 2 or 3% chance that your data is random, right? There's probably a lot of published data that's like, oh yeah, I discovered something, but really it's just, this matter of probabilities. It's not the case, right? But what about particle physics? Now, particle physicists have a really stringent standard. You have what's called a 5 sigma standard, right? Guys, that Z table that we've been referencing only goes up to about 3.5 standard deviations. So that's the highest Z value, right? It goes from like -3.5 to 3.5. And that covers like what 99.98% of all data, something like that. So when you're out here on like crazy so far out on this tail, you're like 5 standard deviations from the mean, right? Then the numbers you're getting from these particle collisions would, if they were not indicating something like a new particle, or you're confirming, in this case, a Higgs boson, or something that had been worked out by theoretical physicists, it would be like on par with winning the lottery. Right? Here I got about a 3 in 10 million chance. Right? He said less than 1 in a million, so it's about on par with that. That being random. Right, so there you go. That's another connection back to probability and statistics. All right, so you guys good so far? All right, so where I paused that last video, paused in the middle of, he was flashing a bunch of these Feynman diagrams on the screen. Okay. I do have a poster for this is hanging up in my room. So this is a simple example of a Feynman diagram. I'm just gonna more or less copy this into one of those quadrants. Okay. Right, so this is the purpose of these diagrams is to show particle interactions. Right, so I got a key for different types of particles. Right. Oh, here we got fermions. It could just be a solid line. We've got, so hey, look, we've got electrons going on here. This could be type of fermions, right? Okay. Photons get their own, gluons get their own, other types of bosons, like dashed off, right? So there's your force carriers, right? Right. And then now almost all the time, like if I had you guys do an experiment in this class, then convention, you usually put like time down on the horizontal axis, right? But the exceptions you guys have seen are, well, do you guys remember Minkowski space-time diagrams? Right, Minkowski space-time, back when we were doing relativity. That one had a convention of putting time on the vertical and space on the horizontal. Okay? And same thing for these Feynman diagrams, right, to represent some kind of particle interaction. Right, so it's just here, right, Feynman diagram. I'm just gonna copy that here, draw these diagrams. Right. So again, gonna put time on the vertical axis. All right, so as time progresses forward, we're going like up the graph, right? And put space on the horizontal. And let's do a key here. All right, so if you see a solid line, it could be any of these fermions, right, which is most of the standard model. Right? See a wavy line, right, that's right, photon gets its own. Right? See like these curly looking ones, gluon, which is one of the bosons. I don't know why that gets its own, but maybe because it's more common than a lot of these. Maybe I'm just guessing. And then other bosons get this dash line. Okay. And so a real simple example could be, hey, what if you have 2 electrons that are interacting? Okay. So this is just one I found out somewhere on the internet. So, okay, this one looks pretty good, right? Right. So, okay, so it looks like they're coming together in space as time moves forward. Right? You have these electrons, I'll label it electron, electron, right? Right. They interact, release a photon, right? And then what? This is just one possibility of how they could possibly interact. Right? Might possibly get positrons out of this. Right? So E plus, E plus, right? So positrons are antiparticles. So they have exact opposite properties of electrons. Right? So they have negative mass, positive charge, right? Because they're exactly opposite of electrons. Right? It looks like I'm drawing error. No, these aren't actually vectors. They look kind of like vectors. They're not vectors, just sign conventions for completing these Feynman diagrams. Right? I mean, if you interpret this as an arrow, it looked like it's indicating the opposite way. What does this mean? Like they're traveling back in time? What does that mean? Right? So if the arrows are backwards, like they look like they're pointing backward in time, what that really means is just an antiparticle. Right? So that's the convention for antiparticle. There you go. So there's real simple Feynman diagram example right there. All right. So you guys ready for quantum computing? All right, quantum computing. Oh yeah.
Do you have a pencil sharpener?
Yeah, right here. Got a couple. Yeah. Ooh, all right. So some stuff I got out of this. He's talking about these qubits. So you guys know computer files are just a string of zeros and ones. Like the video I just played, if you get down to it, it's just a string of zeros and ones, right? And then the computer interprets that and plays the video, right? But these qubits have this superposition of states, both 0 and 1 simultaneously, until of course you measure them. And then when you measure it, it's going to collapse to one or the other, right? So more classical type file, right? Right. So in qubits contain 2 to the power of n classical bits of information. For example, 3 qubits, right? Now, if you thought about 3 bits, okay, it could be like a 110 or a 010 or 101. Right? Okay, so right, so many possibilities. That would be 2 to the power of 3 or 8 classical bits of information, right? And then because of how exponentials work, right, doesn't take too many to fly off the scale real fast. So even like 300 qubits, right? 300 qubits, right? Fewer than the number of days in the year, right? So that's okay. So 2 to the 300 classical bits. Okay. And what is that? That is equal to the number of particles in the observable universe. Right? Now, this is still a developing technology. Quantum computers are not quite there yet. Right? I mean, it's entirely possible that maybe some military agencies or governments have this more developed than they're let the wider public know, right? Because like once this technology becomes fully developed, it's entirely likely to be the case that encryption over the internet is going to be broken quickly. Passwords are all in question, right? So all the passwords used to guard your email or your banking accounts, right? Because like classically how it works, let's say you have a password that's 10 characters long, right? And somebody has to guess it. Okay, well, they sit there and probably like type keys for years and never come across your password, right? But with quantum computers, right, since you have the superposition of states, okay, well, it's 10 characters, right? Well, it could possibly be, any of these characters for 1 through 10, and then it could get to the answer much more quickly, right? Because it works in combinations. All right, so here's a little bit about quantum computing, again, developing type technology. All right, so the next one on the list is Maxwell's Demon and Landauer limit. Now that one's going to take more than the amount of time we have left in class to do, so I'm going to save that one for tomorrow. Now that's a really exciting, fun one. So tomorrow is going to kickstart with the fun one. Here, I'll show you guys superconductivity though to end today. This last one we're going to do is superconductivity. Right. So I think I may mention this a little bit before. Right. Let's do a graph here. A graph. And on the horizontal axis, I'm going to put temperature in Kelvin, like absolute temperature. Right. And on the vertical axis, well, you got a choice. You can either do resistance in a wire in ohms, or actually what I'm going to do is resistivity of a material in ohm meters. Okay. You guys remember a few weeks ago figuring out what is the resistivity of Play-Doh? I think you guys got about 0.2 or 0.3 ohm meters, maybe somewhere in there. Right? Right. So back over 100 years ago, scientists were saying, hey, what happens to the resistance or in a wire or the resistivity of the material the wire is made out of at different temperatures, right? So they tried it at room temperature and they made it colder. Hey, it conducts electricity better. That's less resistance, less resistivity, right? A little bit colder, right? And then they were getting less resistance in the wire and less resistivity for that material. So it was trending down like this. Okay, so that's all fine and good, right? And I came across this really bizarre discovery, which is that it's Sohm temperature, and it's different temperatures for different materials. It calls it critical temperature, T sub C. Well, how about critical? C could stand for critical temperature. The resistance of the wire, the resistivity of the material plummeted all the way to 0, like exactly 0. 0 ohms of resistance, 0 ohm meters of resistivity. Right? There was absolutely 0 resistance in the wire. Right? And that is what superconductivity is. Right? It's this part of this graph, right? Where it goes to 0. Okay? Now, that could be really useful technology. This is one of these technologies. It's not, it has some potential maybe to develop. Right? So crazy things you could do with this. For example, what if you have a superconductive wire in a ring and you just run some current in some number of amps around, right? You could store energy like a battery, and there would be like zero loss, right? Just run around, right? Store energy that way. That'd be one thing you could do with this. The catch though with superconductivity is that this critical temperature is crazy cold for, well, yeah, there are different materials that have been found to go superconductive, but they're all at crazy cold temperatures. And so very last bit of today, I'm gonna flip my screen over and show you guys some graph examples. Graph examples we're gonna look at. Let me find these. Okay. All right, so first graph is what we're just doing here. I don't know what material this is for, where I found this, but here we go. Here's some data showing this going. Critical temperature looks like it's just above 90 Kelvin, which is crazy, crazy cold, right? You know, like laboratory conditions to get that, right? The other graphic I got for you is, right, now this is different materials that have been found to go superconductive by year. So we go from 1900 to, well, almost modern day, right? And then what's the critical temperature for each of these materials, right? Now, one of the big hunts right now is, can we find a material that goes supercritical at room temperature or anything close to that? And at least according to this, the closest we got is whatever this is. This dihydrogen sulfide, I think you would say, something like that, right? This one here. But even that's still crazy. This is like Antarctica level cold. We're talking about just over 200 Kelvin, right? So, you know, like about 300 Kelvin is about room temperature. 200 Kelvin is just crazy cold, right? And even that has this other catch of this is at 155 gigapascals. So it only went superconductive, not only at a crazy low temperature, but also crazy high pressure, right? So you need both those to happen. So not really practical for like a, you know, just room temperature technology, right? So yeah, that's one of those developing technologies there on property. All right, so that'll be a wrap for today. Yeah, tomorrow we're gonna kick off with Maxwell's Demon.